We're very happy to have Daniel Carranza telling us about cubical setting for discrete homotopy theory.
Okay, thank you. Thank you for the opportunity to talk to you guys. I'm very appreciative of having the chance to do this. So, I guess I should say something about so I'll be talking about discrete homotopy theory, which is an area of combinatorics. And it's a homotopy theory for graphs, which is designed to be different from the homotopy theory you get from just looking at a graph as a one-dimensional CW complex. So let's just jump right in. So first, oh, it's already dried out on me.
I'll put it on the floor.
Okay. So first of all, what is a graph for me? Okay, so for me today, a graph is going to be just a set with a reflexive symmetric relation. So it's a reflexive symmetric relation. And it's going to be useful to have drawings of graphs. So the convention is that I'll draw a bunch of circles, which are the vertices of the graph, which would just be elements of this set. And when two elements of the set are related, I will draw an edge between between these vertices. So this would be an example depiction of a graph. What are some graphs that are going to come up for us? So for any non-negative integer m, I'll write Im for the graph with where the vertices are going to be integers from 0 to m. And they're just connected in a line, like so. I'll write I infinity for the graph whose vertices are all integers. And again, these will just be connected in a line, like maybe positive on this end. And they'll be connected in a line, like so. And for a positive integer m, I'll define the cycle of length m to be the graph whose vertices are integers from 0 to m minus 1. Let's say this is m minus 1. And they're connected in a cycle. OK, so those are some happy graphs. Next, I want to tell you about the Cartesian product of two graphs. So if I have two graphs, say G and H, then their Cartesian product. Oh, maybe one thing I should say. Right, so from this definition, you can immediately read off what a map between graphs should be. A map between graphs would be a function between these two sets that preserves the relation. So in particular, since I'm asking that this relation be reflexive, what that means is that graph maps are allowed to send an edge and collapse them to a single vertex. OK. So next is the Cartesian product of two graphs G and H. So the Cartesian product, which I write with the tensor symbol, will have as vertices pairs of vertices where, so I have a vertex in G and a vertex in H. And when are two such pairs connected? I'm going to say these two are connected if two possible scenarios happen. So the first is if their first components are equal and their second components are connected by an edge in H. And the second condition is if their first components are connected by an edge in G, and their second components are equal. Let's just see an example of this. So the example I want to go through is I1 tensored with I1. So I1, right, is the graph with two. Oh, yes?
I guess I'm confused. Are you saying this is the categorical product? Because it doesn't seem like it.
No. So this is this will just be some other monoidal product. Yeah.
Sorry,
Yes. Okay. That was a good point.
The notorians love to call it Cartesian. For some reason,
Yeah. I guess the other name for this that I've heard is box product. And yeah, I think they use categorical product for the categorical product.
But you said the box product?
Yeah, so this is also called the box product.
But they draw it with a circle.
Well, some of them draw it with a box, I think. I choose to draw it with a circle. And I choose to draw it with a tensor, I guess. Anyway. OK, let's do this example. I1 is two vertices connected by an edge. So what should I expect the Cartesian product to be? Well, to start, I want 4 vertices, which are going to be the pairs of vertices. And now this first condition, right, that the first components are equal and the second components are connected, tells me that I should add in these vertical edges. And the second condition, that the second components are equal and the first are connected, tells me I should add in these horizontal edges. And these will be all the edges. So there won't be any edges going diagonally, say, since neither component is equal. And in this definition, I'm mandating that at least one of the components be equal. OK, so once I have a multiplication, I can now tell you what a homotopy is. So if I have two graph maps, F and G, then a homotopy from F to G is going to be a graph map, call it alpha, from G tensored with IM to H, where M is any non-negative integer. And this such that when I evaluate alpha at the left endpoint, I should see F. And when I evaluate alpha at the right endpoint, I should see G. And then right away from the definition of homotopy, you can get a notion of homotopy equivalence. Oh, sorry. Yes. Hi.
This does not seem transitive.
That's a good point. So.
M can vary. Okay,
yeah. I don't know why I struggle with these marker caps. Homotopy equivalence. OK, so we say that a graph map F is a homotopy equivalence. If there is a map back with two inverses. So if there is, say, G from H to G, a homotopy from, say, the identity on G to the composite GF, and a homotopy from the identity on H to the composite FG. OK. Now, I said that this homotopy theory should be different from the homotopy theory you get from just looking at graphs as one-dimensional CW complexes. And now we're ready to see why that is the case. So, okay. The first thing that I will show for you guys is that the 3 cycle is contractible in this world. So meaning the map from C3 to I0 is a homotopy equivalence. And I will do you one better. I will also show that C4 is contractible. So, ditto. So first of all, this should raise some eyebrows because obviously, like in normal algebraic topology, right, the 3 and 4 cycle would be like as one-dimensional CW complexes would be homeomorphic to the circle, and the circle is not contractible. So let's see why it's contractible in this world. Right, so let's focus on the 3 cycle. So if I just draw out the 3 cycle here, right? So I need to give you a map back and 2 homotopies, right? A map back is a map from I0, that's just a single vertex. So this map will just pick out a single vertex in C3. So say I pick out 0. Now one of the homotopies I need to give you is a homotopy between like maps from I0 to I0. So this is trivial. So now I just need to give you a homotopy from the identity map on C3 to the map from C3 to C3, which is constant on the 0 vertex. And this, I claim, I can just draw for you. So what I'm drawing for you right now is the graph C3 tensor I1. And now I can give you a map from C3 tensor I1 to C3 just by, like, I'll label the vertices, and that will tell you where I'm sending them to. So up top, I'm going to see 0, 1, 2. Down below, I'm going to see all zeros, and that's it. That's a homotopy from the identity map on C3 to the constant map at 0 from C3 to C3. So the 3 cycle is contractible here. The thing that you need to verify is that all the edges here really correspond to like edges in C3 here. And now if I wanted to do the same thing for the 4 cycle, so if I just draw 4 cycle like this, 1, 0, 1, 2, 3, then I will do this homotopy now. So now I will draw not C4 tensor, not C4 tensor I1, but C4 tensored with I2. This is what I'm going to draw for you. Okay. Okay, so that's C4 tensor I1, a little like slanted, but so on the top, I need to see identity on C4, right? So I should see 1, 0, 1, 2, 3. On the bottom, I should see constant on 0. And in the middle, I can put 0, 0, 1, 1. And now this is a homotopy from the identity on C4 to, oh,
and the bottom row 0, 0, 3, 3.
Yeah, okay, I want 0, 0, 3, 3. I guess the other alternative is to do, like, I had this at, okay, 0, 0, 3, 3 works. Whoopsie daisy. Thank you for the correction. Okay, but the 4 cycle is contractible if you're not silly like I am. Okay. Now I want to tell you even more weirdness that happens in this world. It turns out that the graph I infinity is not contractible in this world. So this map is not a homotopy equivalence.
Is M required to be an integer in gap? In that gap?
Yes, yes. M is a non-infinity thing. OK, yeah. So I guess people already are cluing into why this is not a homotopy equivalence. But I'll just say in words why that is. So, right, like an inverse would be a map from I0 to I infinity. So that would pick out some integer, say I. And now if you have a homotopy from, like suppose you had a homotopy from the constant map at I, from I infinity to I infinity, and the identity map on I infinity. But that would mean that like if I look at like a vertical strip of this homotopy, like every vertical strip of this homotopy is a path of length m, say, since the homotopy has to have some length m. So it's a path of length m in I infinity. But if it's a path of length m, then there's no way to see identity on the bottom here, because there's no way to get, for example, like I plus m plus like 2 or whatever. It's too far away. So because homotopies have to have finite length, I infinity is not contractible. Which again betrays our intuition from spaces, since as a one-dimensional CW complex, this is R, and R is contractible in spaces. Where am I? OK. So now, like, oh, yes?
I have to know, what about CN?
CN is, yeah, I will get to CN. So the higher cycles, it turns out, are not going to be contractible in this world. I know, really weird. I will get
to each other?
They will be, OK, so they will be, the answer is they will be weakly equivalent to each other, but they will not be homotopy equivalent to each other. Yeah. Super, yeah, very, very strange. Yeah, I guess I'm about to get into why that is. Right, so we need like, we need our first like homotopy invariant here, right? Because we need to know whether like how to tell which graphs are contractible and which ones aren't. So our homotopy invariant of choice is going to be the like discrete homotopy theory version of homotopy groups. So I'll say the nth A homotopy group, and they're called A homotopy groups to distinguish them from homotopy groups of topological spaces. Group. So the nth A homotopy group, maybe I'll highlight nth, of a pointed graph GV is going to be the following. So it's denoted ANGV. And this is going to be a set of maps from I infinity to the tensor power of n to g. Right, so I infinity is this like infinite interval. And when I tensor I infinity with itself n times, what I'm getting is like an n-dimensional hypercube as a graph that like stretches infinitely in all directions. So I'm looking at maps from this n-dimensional hypercube that stretches infinitely into G, but not all such maps. I'm going to demand that this map is just V for all but finitely many vertices in I infinity, I. All but finitely many vertices in this n-dimensional hypercube, right? So like I have this infinitely like stretching n-dimensional hypercube, but now only a finite portion of it like is interesting, because outside of this finite portion, I'm just getting like I'm just constant at V. So really, this is like an finitely sized n-dimensional cube in G, whose boundary is like constant at V. And I'm going to take this set and quotient by based homotopy, which I haven't told you what that is, but if you know how to define like homotopy groups of spaces, then you know exactly how to put together a definition of based homotopy. So this is the right. So the multiplication is yeah. That was the next thing. It's the next thing in my notes. No, okay. what was I going to say? Yeah, I like the activeness. Right, I won't. Sorry, I'm not going to write it down formally or anything, but the idea is that like it's exactly what you would do in spaces. So if I have like two such cubes in G whose boundary is constant at V, I can like concatenate them together, and this is like a larger sized cube, and then you need to make sure that this concatenation is well defined up to homotopy and everything. Hopefully that makes.
And it is.
Yes, and it is well defined. Yes. Okay. Right. So with this definition in tow, we can now compute. So I can compute for, say, the like A fundamental group of the cycles and base it, say, at 0. And it will turn out that for the 3 and 4 cycles, since they're contractible, this is going to be 0. And for all the higher cycles, their fundamental group is going to be Z, which is why the higher cycles aren't contractible in this world. And the way that you would go about proving that. Yes, sorry. Thank you. And the way that you'd go about proving that is you would develop the theory of like covering spaces for this world of discrete homotopy theory. So you'd kind of maybe develop covering graphs. And then you would show that the map from I infinity to Cm, which I'll write as mod m, but that's just wrap around this cycle infinitely many times, is the universal cover. So exactly what you would do in spaces to show that the fundamental group of the circle is Z. And this for large enough cycles. Right, and I guess just to say in words, right, like to answer the question of like, are the cycles themselves equivalent? So it will turn out that all the higher homotopy groups of the cycles are 0, and that in fact I can map from a cycle of size m plus 1 to a cycle of size m. By, say, just like collapsing two adjacent vertices in the cycle. And this will induce an isomorphism on all homotopy groups. But the problem is there is no map back which can be an isomorphism on all homotopy groups. And the reason for that is the map back won't be surjective. And so like it somehow has to kill the cycle, if that makes any sense. Like that's kind of roughly in words what's happening. Yeah. So it's an additional bit of weirdness in this world that like these cycle, like, there's not even like I guess a priori there's not a good whitehead, like at least for these cycles.
Are there any types of graphs where there is?
I guess I'll say not known. It's not known whether there is.
Contractible.
Right. So, oh yes.
One more question. Do we know that when G is connected, AN of GB is independent of B?
Yes, we do know that. Yeah. Right. Okay. So maybe now I'll take a second to say, like, you may look at this and say, well, that's great. It's an exotic homotopy theory and all, but like, is it useful for much? And it turns out that like this theory actually sees applications to like mostly to combinatorics. Like the theory was actually developed by like a group of combinatorialists, which includes like actually Alain Barcelo, who's deputy director of the MSRI. And like they developed this theory with applications in mind to, I think, hyperplane arrangements. I am not an expert on like all the applications, but maybe one thing I will mention is like kind of my favorite application is to like matroids. So my understanding is that if you have a matroid, then like every matroid has what's called a basis graph. And so you can ask, when is a graph the basis graph of a matroid? And it turns out that the answer is it's when it's simply connected, like with respect to these A homotopy groups, meaning it's A0 and A1 are trivial. And there's an additional condition required that like certain subgraphs don't appear in the graph, but like this is straightforward to check. So yeah, there's also applications, I think, to like geometric group theory and TDA more recently, kind of outside of combinatorics, but yeah, it's exciting stuff. But in any case, like, so you want to study these, like, now you want to be able to compute these homotopy groups of graphs. And so, like, one thing that would be useful is, like, can I maybe construct a space whose like, regular topological homotopy groups are the homotopy groups, are the A homotopy groups of my graph, right? So, like, more specifically, is there some functor from the category of graphs to topological spaces such that when I take homotopy groups here and I take A homotopy groups here, this thing commutes maybe up to like natural isomorphism. And so in 2006, Barcelo and some collaborators of hers gave a construction of a functor like this and conjectured that it indeed has this property. And like that's what we were able to prove. And their construction makes use of cubical sets. So let's go over cubical sets. So we can finally see a little bit of homotopy theory, which, you know, I'm excited. So to get us all on the same footing. So maybe I should say, like, cubical sets. So like, I'm guessing people here have seen simplicial sets, just based off of the writing on the board I saw beforehand, which are, right, like, it's like a combinatorial model for spaces, like built out of simplices. And like, it's kind of real, like you do it as a pre-sheaf category on like the simplex category delta. So cubical sets just like are the same thing. It's a combinatorial model for spaces, but now based off of the cube category instead of the simplex category, or the box category, which is what it's called in my notes, and my notes are king. So the box category is a category whose objects are posets of the form 1 to the n, where by 1 I mean the poset with 2 elements, 0 less than or equal to 1. So it's these posets for n greater than or equal to 0. And the morphisms are going to be generated by, they're meaning composites of the following monotone maps. So we have the face maps, which I'd write delta n I epsilon. So this goes from 1 to the n minus 1 to 1 to the n. And here I ranges from 1 to n, and epsilon is either 0 or 1. And this is the map which, given an element x1 to xn minus 1 in this guy, will insert the like epsilon in position I. So I'll go x1, we'll do xi minus 1, I'll insert epsilon, and then I'll keep going as normal. Sorry?
This is x plus 1.
Oh, that's a good point. Yes. Thank you. Right, all these are like shifted down by 1. Okay. So I need faces. I also need degeneracies. And these are written sigma ni. It goes from 1 to n to 1 to n minus 1, where here I ranges from 1 to n. And this is the map which sends a tuple in here to the tuple with the ith coordinate removed. So I see xi minus 1, and I just skip xi and go straight to xi plus 1. And I additionally want the connections, which are written gamma n I epsilon. This goes from 1 to the n to 1 to the n minus 1. Here I now ranges from 2 to n, and epsilon is again either 0 or 1. So this is the map which on a element here will proceed as normal until position I, at which point I will either take max or min of xi and xi plus 1. And then I'll continue as normal. Specifically, I will take max for epsilon equal to 0, and I will take min for epsilon equal to 1. I guess if you're used to simplicial sets, in simplicial sets, you just have faces and degeneracies. But for us, like we're additionally, and I guess, like, oh, yes, question.
Why is I from 2 to n, but then you have I and I plus 1? Would you do either like I from 1 to n minus 1?
It should be from 1 to n minus 1.
Yeah.
Ah, OK. Thank you. Sorry. Yeah, that looks better. What was I saying? Right. So in simplicial sets, you just have faces and degeneracies. But here, like, and you know, the definition of the box category, I guess, varies based off of people's different, like, what they need cubical sets for. But for us, we're going to add connections, which are kind of like additional degeneracies, which will make the theory better behaved. I guess one other remark I'll make is that, like, for the simplex category, faces and degeneracies are enough to generate all morphisms between the like finite linear posets. Whereas here, like, the box category is not going to be a full subcategory of like poset or cat or what have you.
Only answer this like pretty soon, but usually when one bothers with connection, it's because you want the cube category to be a test category. So is that like sort of secretly somewhere in the background? That's why it's better behaved for this end game.
So we will, yeah, like we'll be like eventually we'll be leveraging like the model structure on cubical sets, like the Szynski or Grothendieck model structure, and
Okay.
like we'll be working with like cubical homotopy groups, which do require like they require that you have one kind of connection present. And here it's kind of easy to require both, since like all our cubical sets are going to be coming from graphs, and it will turn out that these just have both connections. But yeah, it's a cool. OK, yeah, so what are the cubical sets that come from graphs? So there is a functor from the box category to the category of graphs. And this will send an object 1 to the n in here, so the graph I1 to the tensor power of n, right? Like essentially the existence of this functor is essentially just saying that, like, you know, these cubes in the world of graphs have like faces, degeneracies, and connections. Like you can write down these formulas word for word, and they give you good graph maps. And so what that means is I can define now a functor from graphs to cubical sets by homming out. So this functor I will call N1, which means the one nerve. So, right. Its formula, so if I have a graph G, then N1G is the cubical set, whose set of n cubes is just graph maps from I1 to the tensor power of n into G, right, with faces, degeneracies, and connections given by precomposition. Okay, right. So now with this construction, I can tell you what the conjectured functor up here was. So the goal then, so their construction is to go from graphs to cubical sets via this functor N1, and then from cubical sets to spaces using the geometric realization, which would be defined it's again very similar to the geometric realization from simplicial sets to topological spaces, right? And so the conjecture would be that this is the functor that you want. So that this triangle commutes maybe up to some natural isomorphism. Right. Okay. Now, how are we able to show this? Right, so I guess I hinted at it earlier, but the answer is the model structure on cubical sets. Right, so the category of cubical sets has a model structure, which, right, the Szynski model structure or the Grothendieck model structure. And this is a model structure which is equivalent to spaces via the geometric realization. But in particular, what I care about here is that the fibrant objects are the cubical set version of concomplexes. Which maybe I won't fully go over at this time, but they're defined by a lifting condition, the same way that in simplicial sets concomplexes have lifts or are defined by a lifting condition. And importantly, a map between cubical sets, say F, is a weak equivalence in this model structure. A weak equivalence. Exactly when its geometric realization is a weak equivalence as a map between topological spaces, meaning it induces an isomorphism on all homotopy groups. Where am I? OK. Now, how am I looping the model structure into this? Right. Well, you may have noticed that I called this, there's a 1 in this notation here. And it's kind of suggestive because, of course, there's no reason that I had to use I1 to the tensor power of n, right? So I can define a functor, for any, say, strictly positive integer m, I can define a functor from graphs to cubical sets by just saying what are my sets of n cubes? Right, they're going to be, that's not what I need, just maps from Im now to the tensor power of n into G. And now, so now I have a bunch of functors from graph to cubical sets. Oh.
I'm just
OK, good.
calling it something with my fingers because that's where you're going because of where you find how you find the Homotopy groups.
That is where I'm going. Yes, nice. OK. Hopefully you'll all humor. You guys all know where I'm going, but hopefully you'll humor me. So where was I? Right, OK. Now, how am I going to relate these functors together? So if I have the m nerve of G and the m plus 1 nerve of G, I can write two different inclusions here, which I call L upper star and R upper star. Okay, now how are these defined? So first I will define a map L, which goes from im plus 1 to im. So this is just a regular old graph map. How is it defined? Right? If I have, so im plus 1, right, is just integers from 0 to m plus 1 connected in a line. Im is integers from 0 to m connected in a line. And now what is my map L going to do? I don't know. I'm going to send m plus 1 over to m. M goes to m minus 1. And in general, I'm going to take like all the things in here. I'm going to subtract 1. Right? So 2 will go to 1. 1 will go to 0. And now what am I going to do with 0? I'm also going to send it to 0. Right? So this is just the map from an interval of size m plus 1 to an interval of size m, which just collapses these left two vertices. OK, but when I have this map, now I can so I can tensor this map with itself, of course. And this will give me a map from im plus 1 to the tensor power of n to im to the tensor power of n. And now with this map, I get a induced map by precomposition. Right? So if I consider the set of maps from im to the tensor power of n into G, I have a function to maps from im plus 1 to the tensor power of n to G. And this is just precomposition by the map L to the tensor power of n. Right? And this is exactly how I'm defining this map L upper star. Right? This set is exactly the set of n cubes of the m nerve of G. This is the set of n cubes of the m plus 1 nerve of G. And this is the definition of L upper star at level n. And R upper star will be defined in exactly the same way, only instead of like squeezing the left two vertices, I'm going to squeeze the right two vertices instead. The intuition here, roughly, like, so at least for n equal to 1, right? Like, what this map is doing is it's saying, like, so what is a path of length m? Like, if I have a path of length m in G, I can think of it as a path of length m plus 1, where the first two vertices happen to be the same vertex. And for R upper star, it'd be where the last two vertices happen to be the same. And now, with this in tow, we are going to Shoop. Meaning, if I have a graph G, then like the 1 nerve of G now includes into the 2 nerve of G by doing L upper star. I can include into the 3 nerve of G by doing R upper star. Right? Let's do L upper star into the 4 nerve, R upper star, and in general, I can, right? So I get this infinite tower of inclusions. And now I'm going to define the cubical set NG to be the colimit of this tower of inclusions. Right? So the intuition here would be that like an n cube in ng is like is an n cube of any finite length in G, where I'm viewing like a finite cube as an infinite cube, which is repeating kind of in all directions. Okay. So now what you can show is that for any graph G, this co-limit cubical set, the nerve, which I call the nerve of G, is a Kahn complex. Maybe I'll just say is Kahn. And that these maps that I gave for you, L upper star and R upper star, are going to be weak equivalences. Is a weak equivalence. And with this theorem, now, you guys know how to prove this conjecture now. Like, so this theorem just immediately gives you the conjecture. Why is that, right? So here's the original construction of interest, right? I'm going from graphs to cubical sets via the one nerve, and then over to topological spaces via geometric realization. And then I'm going to take its homotopy groups, right? I want to compare that to the A homotopy groups. But now, this functor gives me, or this construction gives me a functor not into cubical sets, but into Kahn complexes, which sit inside cubical sets. And of course, to a Kahn complex, I can also geometrically realize. And for cubical Kahn complexes, so this is kind of the important thing about Kahn complexes for us, is that I can define cubical homotopy groups of a Kahn complex, and and these will agree with kind of like geometric realization and the cubical singular complex. So this, again, it's exactly like how in simplicial sets, like you can define homotopy groups of a simplicial Kahn complex, like entirely just using the combinatorics of simplicial sets. And so now, okay, so right, this theorem gives us this functor, right, that it's a Kahn complex. But the second part of this theorem tells me that this triangle commutes up to a natural weak equivalence, right? This triangle commutes just by definition, right? Because this, this triangle is going to commute by, kind of like I want to say by homotopy theory, right? Like you're really using the fact that like the way we define, like using the way that we define these homotopy groups, and that like the model structure on cubical sets like is equivalent to the model structure on topological spaces. And now this will commute by like this is a very simple computation that you can show, like just unfolding the definition of this, that this triangle commutes. But now you're done. We've just proved the conjecture, right? That this thing commutes.
A and this, I guess the left bottom of it. I just remember there's kind of all but finitely many something.
All but finitely something comes from the, like, the construction of the cool.
I mean, so maybe one thing I can say is that like you can give an alternate definition of NG as like you can alternatively say that.
These things pretty much formal. The left and bottom thing is like you just like unfold
Yeah.
categorical definition. And
Yeah.
it works.
Yeah.
Cool.
Maybe, yeah, I guess easy is kind of a bad word to use, but it's, yeah, like just,
You don't use any homotopy theory, it's just formal.
yeah, exactly. Sorry, just to finish I'll just finish my thought. Please humor me. You can alternatively define like the NG, like you can kind of ignore this co-limit for a second and like separately define just some cubical set NG by saying these are going to be maps from I infinity to the tensor power of n to G. And these need to be maps that stabilize in all directions. And I haven't defined what that means. But essentially what it says is that like, there's only a finite portion of I infinity to the tensor power n that's actually interesting in this map. And outside of it, it's kind of like, it's not constant at a point, but like it's constant enough so that you can take like faces of an n cube here, and that's like well defined. And with this definition, like you can then like explicitly show that this will have the universal property of this colimit. That would be like another approach that you can take. And then it's kind of like the way I said it, you kind of see that like the A homotopy groups like are like I start with this set, but now like it stabilizes specifically at one vertex, and then I'm going to quotient by based homotopy, which like will exactly agree with homotopy groups of concomplexes. Yeah. Okay. Sorry. The last thing I want to say is that like when you have this theorem here, you not only can show that this conjecture is true. So like you can prove this conjecture. You can also prove and we did, a like version of the Hurewicz theorem for discrete homotopy theory. So that would relate like the A homotopy groups to A homology groups, which I haven't defined, but they're a thing that you can define that exist. And this tells you what you'd expect, that like for a n-connected graph, like the first non-trivial homotopy group and the first non-trivial homology group are isomorphic, like for like n greater or equal 2. As in the version for n equal to 1 was proven before my time. And lastly, we were able to construct a fibration category structure. Like we were able to give a fibration category structure on the category of graphs, and show that if you have like a fibration sequence of graphs, then there's a long exact sequence of their homotopy groups. And kind of the really cool thing for me in this whole project was that like all of these like really just fall off the bone once you have this theorem set up like in this kind of like world of cubical sets for studying discrete homotopy theory. Yeah, that's all I'm going to say. That's it.
Questions for Daniel?
First one I want to ask is, you have a set, I mean, you probably haven't characterized because this would be like a huge thing to look at now, but I'm wondering, like, are you folks getting closer to characterizing which portion of the world of homotopy types that this n traces out?
It's like, yeah, it's definitely under like active and fierce development. Yeah, like.
Yeah, so the other thing I want to say is not like a question or anything. Like the reason why I was like, oh shit, you're going to do this is because this trick for doing this kind of colimit, like Hahn uses it implicitly because it doesn't have this technology yet back in the 60s to develop a semi-simplicial model of spectrum. Right, the emergent where, specifically he's taking, for like you've got like the stable n simplex and the stable n plus 1 simplex, and he finds maps between those implicitly to be exactly the kind of colimit that you're talking about. Which is like shifting a dimension again and again and again, and taking the colimit for all of those. So like that's just sort of like a fun thing that trick becomes relevant in this context.
Very nice. Very cool. I guess, yeah, like for us, we kind of like, for us, like we kind of landed here by looking at like, if you like, when you prove, for example, the like when you do the Conquillan model structure on simplicial sets, right? At some point you have Kahn has his like x infinity functor, which is fibrant replacement, and like for example, like when actually trying to prove that this is con, like the proof that you end up with, like is kind of a little, like somewhat similar to like how you would show that like x infinity of a simplicial set is a Gon complex, and that, like, you know, it's again this like same type of co-limit, and yeah. But yeah, it's very, I don't know, homotopy theory is cool.
Because actually this, like the X functor is something works for simplicial sets, and it doesn't work for cubical sets. And somehow in this proof, we're able to just recover enough of X functor to not necessarily, permanently replace every cubical set, but those of the form N1G.
Mm.
What do we think then again?